Are we recording it? Let's get started for the second day of this workshop. My name is Michael Mahoney, and I'm one of the co-organizers. And we're very fortunate this morning to have a speaker who's going to be talking to us, who's done a lot of sort of interdisciplinary work in the spaces, and is a nice example of some of the stuff we've been thinking about when we were trying to organize the session. So Animashree Anandkumar is at Caltech and is also director of ML research at NVIDIA. So an interesting interface there. She was at Amazon previously. She's gotten a whole bunch of awards, Sloan Fellowship, Career Award, Young Investigator Award from DOD, and a whole bunch of industrial sort of faculty fellowships, which is sort of representative of sort of the nice interface between theory and sort of industrial applications she's done. So she's part of the World Economic Forum's expert network, and really interested in designing sort of principled AI and ML algorithms and applying them in all sorts of interdisciplinary applications. And I guess she's done particular work on unsupervised AI optimization and a range of tensor-based methods. So today we'll be hearing from her about neural operators for parametric partial differential equations. So Anima, it's all yours.
Thank you, Michael, and thanks for the invitation. I think this workshop is really timely. Broadly, I want to make a comment that it's a great time to be working on AI for science, right? So the application of AI to different scientific applications requires, in most cases, not just a straightforward use of existing methods, but development of new methods, use of domain knowledge and structure. So I think it's really makes for rich interdisciplinary collaborations. I think one key aspect we have to keep in mind is the aspect of zero-shot generalization, right? So unlike other applications where you expect the training and testing distribution to be the same, in many scientific applications, that's not the case, right? You do want generalization to entirely new settings that are not seen during training, because most of the time you are either running in very different settings than what's available in training data. Maybe you're trying to discover new drugs or new materials. So this is not possible to give all that data during training. And so that aspect makes it important to incorporate structure and domain knowledge. So it's not a standard supervised learning paradigm of any function approximation. So that's an aspect that I think differentiates this from standard machine learning. So with that in mind, today I'll focus most of the talk on the series of works we've done on the notion of neural operators. So how we can learn the solution operators for PDEs and any other operators between potentially infinite dimensional spaces, right? So how do we generalize the notion of neural networks which work on function mappings between finite dimensional spaces to infinite dimensional spaces? That's the first aspect of taking a principled approach. And then the second aspect is how to make this work on lots of well-known PDEs, especially challenging PDEs like Navier-Stokes for fluid turbulence, and how can it be much better than traditional methods. So that's the overview of the talk I'd like to give now. And this is interdisciplinary work done at Caltech, with Kaushik Bhattacharya and Andrew Stewart, who had extensive knowledge and background in solving PDEs and using them in so many applications. So the use of all those inspirations from traditional methods was critical towards designing these deep learning based methods. So let me now, so that's the team we have for this work. And indeed, right, so PDEs are a foundation for lots of scientific modeling. There's a set of equations given, and then you want to solve them. I do want to point out that the aspect we are incorporating does not even require equations. You could also be just data-driven and not have equations. But in the beginning, I'll mostly look at the standard solution setup for PDEs, assuming there are equations, there are initial and boundary conditions, and then we have to find the solutions. So we'll go with that setup, and we can ask, how do we now replace traditional methods with deep learning based methods with the hope of much faster solutions, right? The computational complexity is severely reduced, but we still don't give up on fidelity in those solutions, especially across a range of different conditions. So that's the key, that it's not just fitting well to the training data, but it's able to solve PDEs under other conditions not seen during training. And so this generalization aspect is so important. And so that's how we'll frame this problem, where we have a set of input coefficients, right? The coefficients could be like initial conditions, boundary conditions, and other parameters of the PDE. So it's a family of parametric PDE, right? So we'll have neural networks solving it for one family of PDE rather than just one instance of the PDE. And that's the idea. From this input, we want to map it to the solutions, and this is the mapping we want the neural networks to learn. So key difference here is these mappings are generally infinite dimensional, right? So if you look at now mapping the input on any grid, any resolution, to also the corresponding outputs, right, that's no longer a finite dimensional problem. And that's what differentiates it from standard function approximation we have in neural networks. And indeed, a quick comment here is, compared to traditional methods where it's brute force, right? It's not data driven. I mean, it's solving the solution with a numerical approach. And there, each time we change any of the, say, initial or boundary condition, you have to rerun everything, right? So there's no saving on computation. You have to run everything. Whereas with the data-driven methods, the idea is we've learned a good representation from different conditions. So if you change it to now to a new condition, you could still get a fast solution if it's able to generalize well. And that's the important aspect here. Of course, the one caveat is you do still need the training data to first be generated with traditional methods in order to train these neural networks. And that's where ideally we would like to be able to train on coarse resolution data, cheaper data, and directly generalize in a zero-shot manner to high-resolution solutions, right? So training time, if you can get away with just low-resolution data, and a test time, if you can directly evaluate it in high resolution and still get very accurate measurements, then that's a great method, right? Because then this drawback would also be addressed. And of course, in many cases, you may not have data at all. You just have equations. Then can you still use a neural network-based method to solve it? That's another open question here. So, but that's the general, I guess, differentiation between traditional methods and learning-based methods. So indeed, right, so just to kind of reiterate the setup, what we are considering is having inputs with different kinds of conditions. So could be initial and boundary conditions. You get different such inputs, potentially on different resolutions and grids, right? We are not going to assume they're all on the same grid or resolution. And then solve the two, you have the pairs of outputs corresponding to those inputs. So that's our training data. And once we learn this, we want to evaluate it on any arbitrary grid and resolution for the same PDE family. So that's the setup, what we have for operator learning. And that's what, right, this mapping between infinite dimensional spaces, we call them operators. And that's what we'd like to learn. And as I mentioned right in the beginning, that's the important difference, right? So the standard neural network typically does vector to vector mapping or tensor to tensor mapping. But then here we are mapping between potentially two infinite dimensional spaces. And that's what we have to keep in mind on how to learn the solution operators so that you can evaluate at any resolution, at any grid point. So that's the main difference. And indeed, to further think about how to contrast traditional methods with data-driven methods, right? So the traditional methods indeed have complexity, increasing very fast as you require solutions on the fine grid. But as anyone who's worked on PDEs knows, right, there are certain phenomena you can only observe in the finer grid, right? Because these are multi-scale problems. So if you think about Navier-Stokes and the turbulence, the local eddy currents and those phenomenon, you cannot observe it in coarse resolution, right? If you only solve it in coarse resolution, the solution will be very off. It won't be accurate. And so that's what makes this very challenging to be solved by traditional methods. And whereas with data-driven methods, our approach is to come up with a resolution invariant, mesh or grid invariant neural network. So with that, we don't have the issue of complexity drastically changing with resolution. And, we also, the only challenge, of course, is, right, we have to ensure it's trained well so that we can get the solution in an accurate manner. And so that's what brings us to the notion of neural operator. And for that, let's kind of ground the problem a little more. So we'll consider second order elliptic PDEs. This is where we have Navier-Stokes and many others belonging to this family. And to begin with, we are assuming there is initial conditions, right, being mapped to different solutions and also potentially boundary conditions, although in this specific example, it's zero boundary condition. And we want to learn this operator. So the main inspiration now for our method comes from the Green's function. So if you are aware of what the Green's function says is if we are having the inverse of a differential operator, right, that's an integral operator. So hence we can write it as integration with Green's function, right? So for a linear PDE, this is a linear operator, and we can write it in the form of this convolution. On the other hand, the PDEs, and the idea is, yes, if you have the solution in the forms of a Green's function, you can then aim to approximate the Green's function using a neural network. So the notation here, this kernel, what it takes is the location, it takes the initial conditions at each location, right? And then it is integrating over the space. And it's also like looking at the input representation at a layer. So the main idea is we are not now just doing this in one layer, we will do this on several layers. And that's what allows us to solve this not just for linear PDEs, but also for general nonlinear PDEs, right? And this has the flavor similar to the implicit method in traditional PDE solvers, if you're aware. And what it's saying is you're now iteratively coming up with a solution. So you can think of T as the layer in a neural network. So you're solving the kernel convolution in one layer, right? Adding some additive bias term and taking some nonlinearity and repeating it again. So you're stacking several layers of this kernel convolution with nonlinearity. And so that's what would give us now a universal approximator for any operator, right? So we are now able to, this way, extend standard function approximation theory for neural networks between finite dimensional spaces to now infinite dimensional spaces. So that's the main idea. So each now K here is a kernel convolution. It's an integral operator, right? And it's non-local, right? Because now you're doing this kernel convolution on the entire spatial domain. So it's potentially non-local. Whereas the nonlinearity can be very simple. It can be local, right? A simple nonlinearity. Like I think we tried the ReLU and some smoother versions of that. So if you're now composing this over several layers, you will now get the ability to approximate even nonlinear PDEs. And as an additional detail, you can do this all in a lifted space, right? So the input can be lifted into a certain higher dimensional space through a matrix P, and then projected back to the output dimension in the end. And these are, again, hyperparameters to choose, so you can always do this. And so that's the overall notion of a neural operator, that we are combining the notion of continuous kernel convolution with standard nonlinearities. And so we are replacing what we see in a fully connected network, that's matrix multiplication, which is also a linear operation, with now kernel convolution, which is linear but is continuous, right? And you can now express this as mapping between infinite dimensional spaces. And this is resolution and grid invariant if you can approximate this kernel convolution well. And so that's the extension we are seeing. And indeed, you can prove a universal approximation bound similar to what we have for standard neural networks. And what we can show is if the operator is continuous on a compact domain, then you can find a neural operator that can approximate it. It is still an open question coming up with finite sized approximation bounds, right? Similar to what we have in a standard neural network. For a given function, what is the size of neural network you expect? I think these are open problems here, but I think these are tractable. So it's a matter of time when we can come up with also some good bounds to show the approximation. But this is nice, right? So we now have a strong theoretical backing saying that if we can design now neural networks where we are stacking many layers of kernel convolution with nonlinearities, then that can accurately approximate the solution operator of PDEs. So the difference is we are approximating the solution operator and not just solutions of a single instance of PDE. And this way, the solution operator, we can expect it to capture the underlying physics and underlying structure of the problem, compared to if you're only solving an instance of the problem, it is just going to overfit, right? There is no hope for generalization. Whereas by design, by designing it as the solution operator, our goal is then to be able to solve any instance of the PDE for that family. And that's the main difference here, that we can achieve zero-shot generalization to other conditions, other instances of the PDE family, by framing it as learning the solution operator. Yeah, so that was the setup here. Now the details, right? Yes, you can now come up with different methods to solve the kernel convolution. What would be a good one that works in practice, and what other inductive bias can we use? For natural images, we saw that if we can learn the small convolutional filters, local filters, that works very well, right? So what can we do for different families of PDEs? What would be some good inductive bias to design into these neural operators? So that's the next natural question. And indeed, we tried several ones. Making it low rank, like a PCA, is standard, right? You can always approximate it as a low rank matrix approximation. And that's a standard one. We can also do it as graphs, because if you're now doing it as a graph, you can do it in any resolution, right? If you define the graph based on certain distance, right, function, then you can define graphs. And we have also tried like multipole graphs, where you have multiple layers of graphs similar to multipole methods, so that can capture multi-resolution data. But it turns out that all these three are not as good as the Fourier neural operator. So using the Fourier transform to solve the kernel convolution turns out to be so much more powerful than these other variations we tried. The other variants are the first ones we tried with. So only when we looked at the inspiration on what traditional methods are doing, the pseudo-spectral solvers are doing using the Fourier transform. And when we tried it, that turned out to be much more powerful. And so that again shows the role of inductive bias, right? So we have to talk to domain experts, collaborate with them to understand what has been working well in traditional methods and how to build that into also machine learning models. And so what's the reason for this? The main aspect we believe why Fourier transform is so powerful is it can capture global correlations, right? So if you're using like filters in a standard neural network, it's great for capturing the edges of images and other local textures and features, right? So, you're doing it in a very local manner. Whereas if you're trying to solve a PDE, think of the again, the fluid, right, with all different like eddy currents and other flows. There is local, of course, eddy currents, but there's also lots of global correlation connecting them. So you cannot just solve it as a local problem. You need global correlations. And that's where when we were doing graph neural networks, that was just not enough to capture global correlations well. And whereas Fourier transform can do this very well. And indeed, if you're aware of analysis of Navier-Stokes and many other equations, all that analysis is in the Fourier domain, right? We are looking at how along different frequency modes, what is the uh, properties of the solution. So that makes sense that we want to do this in the Fourier domain. And that's where, if you go back to signal processing 101, right, the main aspect is you can now solve convolution in the spatial domain as a product in the Fourier domain, and we can then take the inverse Fourier transform, right? So this way you can now replace the solving of the kernel convolution with multiplying with a weight matrix after the Fourier transform and then doing the inverse Fourier transform. And that's what is a layer, right? What we call the Fourier layer. And what we also do is, the intuition is we want to pick out the low frequency modes because we are going to compose these layers with nonlinearity. So we can get high frequency modes through the nonlinearities, right? So we do pick the ones, we have, what we observe is we do pick the low frequency modes when we train this R matrix, so which is also right what we expect. So that's and then, it's always good to add another bias term, especially if there are non-periodic boundaries that can't be captured very well with Fourier transform. So it's always good to add this additional term, which, the Fourier layer cannot capture very well. And then you do this and you do nonlinearity and then stack many layers of that. So very simple architecture, right? So we are solving this kernel convolution in the Fourier domain and composing it with nonlinearity. And this also resolution and grid independent because you can solve Fourier transform in any resolution and also on any potentially irregular grid, although the standard FFT is still assuming regular grid. You can convert it also to solve irregular grids. So that's the aspect, right? It is now having the resolution and grid invariance properties that we wanted in the first place. So it can learn, we can hope for it to learn the solution operator, especially in cases where we know the solution operator is a low dimensional object. For instance, we know for Navier-Stokes, the solution operator is having a fractional dimension. So it's a low dimensional operator. So even though it's mapping two infinite dimensional spaces, the operator itself is low dimensional. And hence we can expect it to be approximated well with a decent sized neural network. And that's why we can hope for learning to happen. So that's the overall approach. What we do find is we were surprised at how good this method works. It's a good, pleasant surprise whenever that happens. That we trained it on less than 1,000 samples of different initial conditions here for this 2D Navier-Stokes. And we trained it using very coarse scale data. So just like spatial resolution 64 by 64 and 20 points in the temporal space. And at test time, what you're seeing here, we're directly evaluating it on the higher resolution. both spatial and time resolution. And that's what makes this very powerful, right? We can have very quick training, cheap training. We also realized we didn't need a lot of samples to train this, and we can directly evaluate it at the higher resolution. And as you can see, it is able to capture all kind of turbulent flows very well. And it's not just pretty pictures. It also turns out that it can capture the wave numbers very well. I think the difference is this is one run versus this is some kind of average. I apologize. The caption is missing here. But what we find is the ability to capture the wave number is also a good one. And yeah, so we did compare this with other machine learning based methods, but only when the training and test sample is in the same resolution, right? Because the other approaches do not generalize to the setting where you have a higher resolution text time data. And even in that case, we observed that the Fourier neural operator has extremely low error compared to the other methods. And Burgers and Darcy-Flow are simpler equations than Navier-Stokes. So that already tells us that the Fourier neural operator stands out among the pack, right? It is certainly something special compared to the other methods. And of course, it can do zero-shot super resolution that the other methods cannot. Yeah, so we use this to solve Bayesian inverse problems, right? So this is very much we come across in so many settings where you don't know what the initial condition was. You roll out the simulation and you get the final condition, right? So the idea is this would be something that you observe in nature, right? And then you want to get back the initial condition. For instance, in seismology, this could be observations on the surface where you measure and the initial condition is somewhere deep inside the earth that you cannot measure, right? So you want to be able to estimate that. And this is expensive for traditional solvers because what you would do is a standard MCMC method where you start with some random initialization and then run out all those forward trajectories. So lots of forward evaluations, right? And then you update the posterior and you do this many times. So this is very expensive because it requires lots of forward evaluations, which requires access to a simulator of the PDE. And so you can see our method is able to capture very similar, not just pictorially, but also in terms of the accuracy, similar numbers as the traditional method. So it can get the posterior mean estimate of the initial condition, which is the best you can do, right? Because this is ill-posed, you cannot exactly invert and get the initial condition. The best you can hope to do is capture the posterior distribution. And indeed, if you do the forward simulation from this initial condition, you can get to the, you can reconstruct the final solution that you've seen as accurately as the traditional method, but with a very big speed up. So that's the key here. We can solve really fast compared to traditional methods because we are able to now do all these forward simulations very fast. And so we can solve a lot of challenging inverse problems in this way. So we also wanted to address another aspect of it because, so far I showed you the inverse problem. I showed you this kind of the ability to solve the equations, right, over certain spatial and temporal resolution. But then if we want to capture the trajectories that we've observed in a data-driven manner, these are systems that can be very chaotic. So you cannot exactly reconstruct the trajectories that you've observed for a really long time. So instead, what we want this to capture, if it's learned the solution operator, is the invariant measure, which has the underlying statistics, right? Could be in terms of autocorrelation or other statistical measures. By capturing that invariant measure, we've learned everything we can about solving this equation. So this is another measure of asking, can we capture the solution operator very well using neural operator framework? And for that, we started with this popular 1D KS equation. It's a kind of oscillator equation. And in this case, what we are doing is we are just learning the neural operator for one-step transition, right? So all it's doing at training time is only seeing one-step transition. It's no longer seeing the full trajectories of the longer-term evolution. And the question is, can it, by composing this one-step operator many times, can you capture now the invariant measure? Can you accurately capture the statistics of evolution over a long time period? And that means we've learned the solution operator if we can do this well. Because what the underlying theory says is this is a Markov operator. All you need to do is learn this one-step transition operator. And if you compose that as many times as you want, that gives you the solution at any time point. And these are still ongoing works. And what we see is the Fourier neural operator is able to capture it much more effectively. It's able to track the ground truth to a much larger extent, even though it's been trained only on one-step transitions, right? It has never been trained on longer trajectories. Whereas, other forms of recurrent networks such as LSTM and GRU don't capture it as well because they are, don't generalize very well. So that's the aspect that, by again thinking about the invariant measure theory and knowing that all you require is this Markov operator and being able to learn that in a resolution and grid independent manner, we can capture the invariant statistics, the statistics of invariant measure very well. So we also applied it to many other settings. Plasticity is one of them, and Kaushik Bhattacharya, who's been our co-author, is an expert in this setting. And ultimately, we want to be able to discover new materials with desirable plasticity properties, right? Hardness properties. And this is very complex because it's multi-scale. Again, I won't attempt to explain these exact equations, but the idea is there is the strain and the stress and the force you apply. And the question is, how accurately can you predict the stress? And this is where we use the neural operator to replace traditional solvers in the fine scale, but we still use the traditional approach for the coarse scale. So unlike the previous setting where we learned everything from scratch, for a complex multi-scale problem like this, what we decided was to do this replacement step by step, right? Which makes sense. Again, we don't want to throw away all the domain knowledge. So keeping that within the framework of a coarse resolution solver and replacing the fine scale with neural operator meant we can solve it so much faster, in fact, even much faster than the previous setting we saw. And that's also because a lot of code is legacy code in these kind of traditional methods. So it makes sense that by leapfrogging to using GPUs and using the latest tensor cores, right, in GPUs that can have a huge speed up while maintaining accuracy. And so what you see here is a visualization of stress as a function of thickness for different material thickness here, and it can accurately predict that. So this is very important in a lot of applications. Yeah, so the main takeaway I wanted for this section was to show you how we can extend the notion of function approximation in neural networks to now infinite dimensional spaces, what we call operator learning. And one of the applications of that we've seen is for learning the solution operator of family of PDEs. And but with this, what we can do is learn it in a completely resolution and mesh invariant way. The Fourier operator turns out to be the most effective one because the inductive bias is great for many of the popular PDE families. And it's also fast. Having fast Fourier transform is a great also aspect for speed. And it works much faster while maintaining accuracy, generalizes very well. And in future now we are planning to scale this up even further to much larger scale problems and much more real world settings involving turbulence, involving all these material properties, so many different range of applications. So I'll take a break here because after that I want to show other instances of AI for science where we can combine domain knowledge with learning methods. But before that, I'm happy to take questions.
Yeah, so there's two sort of questions. This is a natural break point, so I'll ask them, and then if there's anyone else that has a quick question, it sounds like this is also a break point. So one is how much, this is about 4 minutes ago, so on your slide or two back, how much is this in terms of the Lyapunov time?
Which here?
And
I asked the question, yeah, it's about the chaos
Yeah.
equation. Because these are time steps on the vertical axis, or?
Oh, yes, those are time steps. Yeah. Yeah, so sorry, what was the?
So how much is this in terms of the Lyapunov time?
That's a good question. I guess, yeah, I'd have to get back to you on that because the conversion, yeah, I'm not sure about that.
And what about the initial error? Because the initial error seems to be higher on the Fourier neural operator, but then it seems to sort of be more stable or resistant against that error.
Yeah, that's a good question, right? There are a few artifacts here. That's also not so clear because ultimately, you know, we know in these chaotic systems, we don't expect to capture the trajectory very well, right? So, I mean, there's certainly a correlation of getting low error here to also capturing the invariant measure, but it's not perfect, right? So I think the aspect that it's going for a longer time step, but somehow maybe not always driving down the error here to zero. I think it's a kind of trade-off it's doing, but yeah, we don't have a deeper understanding on that. That's a good point.
All right, thanks.
And another question was, did you, about 2 minutes ago, did you compare the times on the same hardware? When discussing the plasticity, it sounded like the FNO was tested with GPUs, yeah. CPUs, while the legacy code was CPU. Were there any timings done on things like Daedalus with distributed GPU?
Yes, yes, and that's why we, you know, it's still like done because, you know, it still has to talk to the core scale, right? So there's still a lot of GPU CPU exchange because, right, we haven't replaced everything with GPUs. So we haven't made the code super efficient either. But yeah, there's a lot of low-hanging fruits, and our goal was not to exactly benchmark the two because we know even that would be several orders of magnitude speed up, right? But ultimately leapfrog and get away from traditional legacy code, both traditional methods and legacy code. And so that's why I mentioned that, like why have such a big speed up.
And Murad had a question. Murad had a question for the end of the talk, but maybe if this is a natural point, you could interject it now, I guess.
I could wait, doesn't matter.
Okay. Okay, so any others?
Could the Fourier transform be compared with a reduced order methodology where the kernel select the most important modes, and how does the kernel work in irregular boundaries?
Yeah, that's a great point. We have been now testing that. That's one of the student projects for the course. And so far, we haven't seen a big advantage there, but you know, there are still conditions that they have to test extensively. So yeah, that's on the pipeline.
Where does the finer scale information come from if the method is purely data driven and the training data is generated from the course simulations?
So, I mean, the idea is it can't be way too coarse, right? I mean, there's certainly a threshold above which if it's too coarse, then you can't expect to learn the solution operator. So you have to kind of experiment with that. because the idea is we are also now training it across different initial and boundary conditions. So it's able to learn the generalization even if the data is coarse. But yeah, it can't be too coarse, right? This is something we have to experiment with and see what is the best, what is the minimum resolution needed to get good generalization.
And it looks like there's one more. Is this related to random Fourier features?
So, I mean, that's right. If you want to like approximate any kind of kernel, you can use random Fourier features. But here we are directly using the Fourier transform, right? So yes, both are operating in the spectral domain. So in that sense, I guess it's similar. But then we are not doing any kind of random sampling here.
And is there a guarantee that the method satisfies physical conservation laws?
Good question. So far, we haven't enforced those penalty terms, but in another work, we are now combining it with those penalty terms. And again, this is ongoing work, so we are, I don't have precise results on how much that improves the solutions.
So, Anima, I wanted to ask a question about the point you made about infinite dimensional versus finite. First of all, very impressive work. Thank you for the talk. I mean, you said you were surprised how well it works. You're not alone, because we have been trying this method on some other problems, and we are actually seeing a lot of promise in it. But we don't understand the limitations quite well, and I'm hoping you can help us understand that. So one may argue that instead of using not necessarily finite element generally, but local basis functions that gives you that vector that you discussed at the beginning, you're now using harmonics or spectral basis functions, which is also, you will be limited by a finite number of them. And you're at the mercy of Shannon's theorem, which relates still the highest frequency you have to the basically sampling density that you have in the physical domain. So that's probably one way that this limitation may come in. And the other part is that when we have discontinuities like shock waves or phase interfaces that we care about, Fourier transforms may not capture discontinuities well, and you get Gibbs phenomenon. Can you maybe say a few things about these issues, if you have faced them, or how you would handle them?
Yeah, absolutely. Those are great questions. And after I answer, I'd love to learn more about what applications you're trying this on. So for the first aspect, I mean, there is certainly there's no free lunch, right? If the solution operator itself is high dimensional, you do need a big size neural network. So now we are scaling up to 3-dimensional Navier-Stokes. Earlier, what I showed you was 2-dimensional, right? So we need now much bigger neural networks, and we try to compress. For instance, we said, if you don't bring it back to spatial domain, right? So remember, we are doing inverse Fourier transform, and then doing nonlinearity, and then going back, right? So what if we did many layers of just Fourier in the Fourier space itself, nonlinearity? And it's not as effective. And my intuition is, again, because of the time frequency uncertainty principle, right? So you want to bring it back to the time domain and do nonlinearities there. Otherwise, if you're just doing it in the Fourier domain, right, it's not kind of, because you do want some kind of local activations in the spatial domain. You can't do it very well in the Fourier domain. And then it's inevitable, and now we are planning to design a model parallel approach where we can divide up the network into multi-GPU and ultimately multi-node. So I think, yeah, that's where, right, and that would then allow you to capture much more frequency modes, right? Otherwise, you're limited by the size of that to load into the GPU memory. So that's one aspect. For the second one, when there are discontinuities, we've tried with wavelets, especially I think Darcy in some extreme cases, there is some, but again, right, those are like the kind of fluids we are looking at. They don't have a lot of discontinuities. So I'd love to learn a use case where they could be much more effective. But I think it's natural to think of wavelets, right? Because that's precisely what they're designed for, where there's both smooth phenomenon as well as sharp discontinuities.
Thank you.
Yeah, so I was curious, what application are you trying this on?
Well, some we have been trying to apply to multi-phase flows and as they relate to 3D printing application. I'd be happy to talk offline.
Okay,
more.
great. Thanks, Moran. Yeah,
I'll send you an email. Sure.
talk more.
A question is, the methodology to learn inverse mappings is exactly the same as that for 4 problems, or is there some change?
Yeah, so far we've done the simplest thing, right? We just did the standard MCMC. So yeah, just doing the forward maps and updating the posterior, but there is a potential to also do it data-driven and maybe, like also try to learn the inverse mapping directly. We haven't explored that so far. Yeah, but again, a good question. I think there's a lot to explore here.
How well does it deal with noise?
So again, depends on what kind of noise, right? I think, so far we've done it, this deterministic problems. I think we've tried it on simple stochastic differential equations so far. And, it could even generalize much better there because, sometimes, yeah, the stochasticity actually helps. But we haven't explored a lot there. Again, that's something I think that's open to for further exploration.
I don't see anything else. You took a break and had a bit more. I think we have 11 minutes. So if you wanted to get back, but this was a good break. It sounds like for everyone.
Sounds good. Yeah, thanks for all the questions. And again, feel free to reach out if you want to discuss in more detail. So I want to show a few other works that combines domain knowledge and structure with data-driven methods. I mean, these are, by the way, code and blog posts that can help you quickly get the ideas, while the detailed papers are also there. So yeah, the other one that's very related is it's also mesh free, but it's instead of learning from scratch, which is very hard, what it does is super resolution, right? So it is assuming a solution in the coarse resolution given by a traditional solver, and then it resolves it to find the finer resolution full solution. And this is the result here that appeared in supercomputing conference that, as you can see, the model prediction lines up very well with the ground truth. So what it gets is only the low resolution input, and it's able to do super resolution very well. And for this, it turns out because, the super resolution is still a fairly local phenomenon, right? If you're now getting samples all over the space in coarse resolution, doing the super resolution is still fairly local. So it's like what we are learning is a good interpolator. Instead of traditional interpolation methods, what we are doing is using a UNet to now figure out the solution, so learn the good representation. And then the output, again, we want it to be able to query at any point, right? So that's what we call it, a continuous decoding network, be able to learn the interpolation function for any point given the grid points available at the output of the UNet, which is called the latent context grid. So, there are some similarities to the neural operator, right? But also the main difference is we are still doing a traditional UNet here compared to Fourier transform, because it turns out that these are still fairly local phenomena. Recently, we've also replaced the UNet with Fourier transform, and the performance is very similar. So, so I believe for the super resolution problem, the global correlations don't help very well. But for other cases, it can. So this happened before the Fourier neural operator, so this predates it. But again, we found a lot of really promising results by also adding the PDE constraints, which earlier we discussed, right? So, and these PDE constraints you can kind of conveniently, right, differentiate through and get the penalty terms and add that. So you can have both of these. And yeah, that's the overall setup, having the unit, combining it with a convolutional decoder, and ultimately, right, so the baseline is just the convolutional decoder, right? It's not continuous decoding, whereas ours is learning a continuous interpolating function, and that turns out to be much better than the baseline. And this one, again, it's very scalable because we have lots of efficient implementations for units and other deep learning based models, and you can do multi-node. You can scale it up to 128 GPUs. This is the Cori cluster in the Lawrence Berkeley lab, and we get very good efficiency numbers. And so this is now a much larger scale than what we've seen in the earlier case, but it is assuming inputs from a known solver. So that was one of the other works that also, right, in a similar space. Another example I want to show is in the space of drug discovery, right? What we want to do is search for really effective molecules that satisfy different properties. Could be solvability, could be some kind of binding properties. And so this is the main first bottleneck, right? Of course, that's a huge process of doing the full drug discovery, but the first one is you're searching over 10 to the 60 compounds and this huge search space, and we've hardly explored, any meaningful part of the space so far, because so much of it is just the domain knowledge of, we already know some known drugs and we're discovering in the neighborhood of that to develop others, and very high failure rate. So if we can even speed up the first part and search this more effectively and use the underlying quantum calculations to accurately predict the properties of molecules, then we can hopefully get much better candidates for all different stages here. And this is the project with collaboration with Tom Miller at Caltech. And what we are seeing is quantum features are really effective when combined with deep learning, right? So instead of using deep learning end to end, again, combining it with domain knowledge is so crucial. So that's because we want to, train on small molecules. The goal is there's 10 to the 60 molecules. We can't possibly keep training on very large protein molecules with lots of atoms, with thousands of atoms, right? And this is all, first of all, training such a model on large molecules will also be like having overfitting from problems. So with that, what we did was to use molecular orbitals, which essentially calculates the dependence of every atom on the other atoms. And this is highly transferable. This kind of calculation would be invariant whether it's something as simple as a water molecule or very complex like a protein molecule, right? And this is what gives the invariance because of using this molecular orbital. So that's the first thing we do, is capture molecular orbital features and then build the graph neural network by thresholding neighbors within the molecular orbitals. So the idea is you're not just looking at immediate neighbors, which is what many graph neural network approaches have tried for modeling molecules. This, I think, is a very bad idea because you will ignore all these very long range correlations, right? I mean, even if I think some form of benzene or these molecules, you already know it's not just the immediate neighbors that matter here, right? The neighbors, which, I mean, the atoms that are further away also have a big impact or influence, right, for on the atom here. So that's why it's important to capture the long-range correlations, and the molecular orbitals are an effective way to do that. So building graph neural networks on top of those features really enables us to get universal representation of molecules. So we're able to directly predict properties of molecules, right? Get again 1000x speed up which is very impressive. So the DFT is the gold standard there, and we can do even better than that sometimes because we are data driven. So you can both do like kind of pre-training in an unsupervised way without having any supervised data for property predictions, and then combine it with supervised training. So you can do this very well. Another example is the drone landing, which again combines model-based control with a deep neural network to learn the ground effects, which is the turbulent forces, which are very hard to model. So you can now, by combining it with known controllers and known physics and adding neural network, can help it land much faster but safely. And you can do like really close trajectory tracking and stuff here. So, which you couldn't do with just the baseline controller. So I will skip this. There's also like lots of other aspects of combining like traditional control with physics and with neural networks. But the main idea is now we are having so many possibilities in AI for science to combine all the rich traditional knowledge with deep learning and to build principled approaches that combine best of both the worlds. Thank you.
You do not. Okay. All right. Thanks, Nima. That was great, actually. We've done a bunch of work in that area, so it's nice to see you. And we're familiar with some of your stuff, so it's nice to see it sort of brought all together in sort of an overview. Nat had a question about 5 minutes ago for the problem regarding mesh-free flow net. What's the test and training data? It looks like you trained to reproduce Rayleigh layer instability. Can you get super resolution on a different flow?
No, it's on the similar, the Rayleigh-Bernard flows, but different Reynolds number. So different initial inputs, right? The initial conditions.
Did you also use Fourier transforms during the message passing for the drug discovery problem?
No, not so far, just standard graph neural networks. So again, right, so here I think the molecular orbitals are doing the notion of basis, right? They are the right basis because they capture the invariance of how each atom depends on all the other atoms in the molecule. So it's capturing that very well.
All right, so I don't see any other questions, and I think we have a break for 10 minutes. So I'm going to suggest to give everyone a break to stretch their legs or something. We call it good, and thank Anima again. And thanks, Anima, for joining us here and for the great talk. So we have 10 minutes, and then we're going to start up with, I guess, a non-parallel session for 2 or 3 talks for the remainder of the morning. So. So let's call it a break and be back in 10 minutes.
Take care, everyone. See you.
So Nima, have you looked at, if you haven't hung up yet, are you still there? Have you looked at, the operator is more than a function, right? There's the compositional aspect of it. It's a matrix transform. You can, it has to satisfy the sort of compositional property. Was there anything in there that, like for example, the representation theorem that I think was, I don't know if you said you had a separate one or if you just were pointing to the one that the Brown people had, but this, my understanding at least of what they have is this is just a statement about an operator, not sort of respecting its compositional property. Was there anything in what you were doing that focused on that particularly, or was it, or not? Do you know what I'm talking about?
So when you're talking about compositionality, do you mean it over time, like a transition kernel, like what a?
Yeah. I mean, well, yeah. I mean, it's more than a vector, right? Because it satisfies the vector properties, but it also satisfies the matrix multiplication, or F composed with G property. And so, the operator. My understanding of the sort of existential results is that it doesn't sort of take it into account that explicitly. I mean, maybe in some limit, if you get the operator exactly, it does, but in any more robust sense of the word, is there anything in what you have that when you're learning the operator that sort of takes into account that compositional property particularly?
I mean, not explicitly, right? Because, I mean, even if you think of standard neural networks, right, even in finite dimensional space, there's no explicit notion of compositionality, right? Because everything is about just a two-layer network and about the basis expansion. And in principle, you're just extending that, right? It's just that instead of the sinusoid basis you had for finite dimensions, you have now these basis functions in infinite dimensional spaces. And then you can argue the neural network can approximate these bases, right? So that's kind of the similar principle, right, for both so it's yeah, at least intuitively, it's the extension kind of, it's the same philosophy as finite dimensions. And that's a good question, is if it can capture the invariant measure by like learning the transition kernel. Yeah, I don't know how we can prove something about that. That's something we are still doing, you know, also.
Yeah. So that's a harder thing than I was asking, but certainly that was in the back of my mind, because if you could do this thing, then that's one reason why you do it. Yeah. Okay, good. No, I enjoyed that.